Hi, this is Jeff Lendermon. I'm an applications engineer for GoEngineer. Welcome to my webinar on controlling plastic part warpage and SOLIDWORKS Plastics. I'm intending to show how we can control plastic part warpage and see the analysis using SOLIDWORKS Plastics. So each step an engineer would take in the plastic molding process, we can also show that in the SOLIDWORKS Plastics simulation package. In my presentation, I'm going to define what is plastic part warpage. We will look at the causes of plastic part warpage, and I will talk about how we can control this warpage and do this by showing the analysis in the SOLIDWORKS Plastics software. So what is plastic part warpage? In any molding process, plastic parts, shrinkage is inherent in the injection molded plastic part. And warpage is the deformation that occurs when you have uneven shrinkage in different areas of a plastic molded part. So shrinkage will always be there with a plastic part, and warpage is just part of this. So what we have to do in the injection molding process is learn how to control the warpage. So in learning how to control the warpage, we need to know what causes the warpage. One of the first things is non-uniform mold cooling. So when your injection mold cooling system is not designed properly to give uniform mold cooling between the A and the B sides of your part, there'll be areas in the plastic that are retaining more heat and will cool slower, which will cause the part to warp. Another item that could cause warpage is our material characteristics. Some of our materials, amorphous materials such as ABS, polycarbonate, and polystyrene, they have a lower shrinkage rate. This makes them less prone to warpage because they shrink more uniformly. And then semi-crystalline materials such as polypropylene, polyethylene, and nylon. And these all have a higher shrinkage rate and will make them more prone to warpage. We also have, in our processing of injection molded parts, we can control warpage or create warpage with our settings with our injection molding machine. So if we have excessive packing pressure during the molding process, if the parts are overpacked, the system's trying to force too much material into the cavity, which will cause excessive molded in stress. These molded in stresses will lead to warpage as they relieve during the cooling process. Sometimes the stress relief can go on until the cooling outside the mold for days or even weeks sometimes, or if they were subject to exterior conditions, they'll also cause those stresses to relieve and warp more. So in the molding process, we want to control the amount of stress we mold into the parts. With that being said, we can also have warpage caused by inadequate packing pressure. So you have a window between excessive and inadequate that you have to hit that window in your injection molding process to be able to control your warpage as well. Another thing is our part geometry. So if in the plastic part mold design, our goal is to design a part with the most uniform wall thicknesses. So if we have non-uniform wall thicknesses, it will lead to part warpage as well, because the thicker areas of your part cool at a slower rate and they'll shrink more to cause the part to deform. And finally, our gate locations. Our injection location into the part can also be a contributor to some part warpages. Some of the materials will shrink more in the linear direction, which is along the flow path, than they do in the transverse direction, which is across the flow path. This also creates the non-uniform shrinkage and is susceptible to warpage. So planning out your gate locations is another way to keep warpage in check on your part. How can we control warpage? Well, with the SOLIDWORKS Plastics Simulation Warp Study, we can use the software as a tool to help you predict the warpages within your part. We can evaluate different materials. So with over 4,000 materials in the database, we can evaluate the different materials and see which provides the least amount of warp. We've got amorphous and semi-crystalline materials in there, and you can set up different versions of your part with those two materials and compare the warpage between the two. The other thing we can do is to determine best gate location. So you have the ability to go in and try different gate locations all around your part without having to go through the whole mold process and molding them, you can do all of this ahead of time to find the best gate location to control your warpage to start with. We can also control warpage with our part geometry, as I said earlier, trying to design your part with uniform wall thickness, or sometimes we want to control part warpage. We can actually add ribs within the part or change the geometry other ways. This can all be done inside the SOLIDWORKS Plastics software as well by creating different configurations of your geometry. And finally, if we design proper cooling channels during your mold design, we're also able to analyze those within the SOLIDWORKS Plastics software as well. So we can run a cool study along with the warp study and get the results that will identify areas that could cause non-uniform shrinkage. So we'll be able to see hot spots in the mold where you can modify your water lines to cover those areas better. You can add bubblers or different water channels as well and simulate that in the software. So this is just the grid of the SOLIDWORKS Plastics packages, Plastic Standard, Plastic Professional, and Premium. What I'm covering now with the warpage analysis is part of the Plastics Premium package. And now I'll jump over to the software. And basically I've set up just a simple flat part. Imagine trying to mold this and keep it as flat as possible, like a hinged drive door on a CD drive is what it's modeled after. So the first step in running a plastic simulation study is meshing the model, which I've already done all of these ahead of time. So I've meshed this model. I've selected a polymer, in this case, in my database. I've selected a generic polypropylene. So a polypropylene is a semi-crystalline material. We'll try it with that first. Your next step within the process is setting your fill settings and pack settings, picking your injection location. In this model, I've got my injection location in this area right here. And after we've done that, we can actually go through, after assigning those three things, we can go through and run the study, which I've run these ahead of time as well. So just to get a baseline of how much warpage the part is, I've got everything set default, selected the semi-crystalline material, so we're expecting more warpage. So if we go straight to the warp results, since I'm concerned mostly with the flatness, I'm going to look at it in the Y direction only. I'll look at the absolute value, and I'm going to bump up the deformation scale to 20 to actually exaggerate, so it really looks warped, and we can compare those. If we look at the maximum warpage on the part, we've got 0.567 millimeters. So it's quite a bit. So within SOLIDWORKS Plastics, we have the ability to go in and duplicate our study. If we just select duplicate study, we can come in and change parameters and everything. So that's what I've done in this case. And I've got all of these studies that I've run. We can go in and set up and run a batch study of all these what ifs. So I ran the study of what if we change from a semi-crystalline to a amorphous. I've picked a generic PC-ABS blend. We can go straight to the results for these. I used same mesh, same gate location and everything on those. We can actually look and see the flow of the plastic through the part. We've got the ability as well. We can look at residual stresses at the post-filling end. As I said before, a lot of your residual stresses could also cause warpage. So that's another thing we could be looking at to reduce the amount of residual stress in our part. I'm going to go straight to the Y direction again. Change my deformation scale to 20 again. We can see the warpage has decreased quite a bit. I mean, we went from 0.567 and we're a whole lot less now. The absolute value. So we're 0.187 millimeters now. So that's about 7,000. So that's a lot flatter. Sometimes the flatness tolerance may be 5,000. We would still be over tolerance for this part. But to decrease it from 22 thousandths to 7 thousandths just by changing material is really good. So as I mentioned before, there's other ways that we can control warpage. I set up another study. Let's add a rib to the part. So I'm going to load the process of adding a rib. And if you notice, these are all configuration of the part in SOLIDWORKS. So I just added the rib geometry in SOLIDWORKS and go back in and remesh the model to catch the mesh of the rib. All my other settings are still the same. My gate location is still the same. And I'm still using the PCABS material. So it's really simple to do all of these what-if studies with configurations within SOLIDWORKS. So we'll go in, open it up again in the warpage in the Y direction. And even with the deformation scale at 20, we can see there's a whole lot less bend in this part by adding the rib. Now our stress displacement in the Y direction, so our warpage in the Y direction is 0.0506. That's even less than our previous one. So adding a feature and adding a rib, that's another way that we were able to control warpage. In this case, it's a small part, so maybe adding some material by adding a rib would be sufficient. If we wanted to try to keep our part costs down and reduce the amount of material, maybe we need to try a different gate location and see how that works. So I'll go in and change to my gate location. Once again, it's modeled, same mesh and everything, except I set up this part to have an end gate. So I'm changing the flow direction. Instead of across the part, it flows more directly through the part. And we can look at the flow here. And once again, we'll go to our Y, look at our deformation scale at 20. You can hardly even see it move even by doing that. So we have a 0.0202 millimeters warpage in the Y direction. So that's what 0.0008 inches. So that's really, really good. Another thing that I also did in this setup at the same time, we were able to change our fill settings. All of my other studies so far were set up for 100% fill before the pack stage. So as I was saying before, when we can control the packing to keep the part from being overpacked, doing a scientific molding study, typically the situation and the concept is to switch the pack phase prior to completely filling the part. So we're able to simulate that as well in the plastics simulation software. So I was able to go in and change my flow pack switch point to 95% when I did this as well. So what that does is reduce the amount of molded in stress. It's not trying to fill the material cavity completely during the fill stage. And what this does in the actual injection molding machine, it makes up for inconsistencies with your viscosity between material lots, or if you're adding regrind to your material, your viscosities will change some. So by changing your process to where you're changing from your flow pack switch point, it makes up for these. It keeps you from overpacking the mold and flashing the part, and it also will help. It utilizes the pack phase to finish filling it and at a lower pressure, which reduces the amount of warpage. So our next configuration, now that we've done some basic changes, we've decided that our gate on the end is a whole lot better place to go. Within SOLIDWORKS Plastics, It's always good to run a cool study along with your warp study. If you don't run a cool study and have a designed cooling channel in your model, what the simulation software does is it naturally assumes that your mold wall cavities are absolutely equal all around the part. And we know in the injection molding process, we've got water lines running through different channels all in different areas. Some mold designs may have water lines that zigzag back and forth across the cavity. Well, as they do this, they're also pulling off heat from the injected molded part and getting hotter as it goes through. So if you have multiple cavities, one cavity may have more heat on one side than the other, or you may have more heat on the A side or the B side. So our simulation software has the ability to simulate this as well. When we set it up, we're able to create our water lines off of 2D sketches, or we can also model the water lines in 3D. We have the ability to create a virtual mold. So this mold visibility, if I mesh the model, it shows the meshed mold cavities in our water lines. SOLIDWORKS 2018 has the ability also, we can mesh now the solid bodies, so we can actually have 3D body mold inserts in your 3D water lines as well to do that as well. So I'll turn off the mold visibility on this one. So since we've run a cool study, I'll go over and look at the cool results on this one. I've set up this one to have equal cooling distribution in the top channel and the bottom channel. So it's still consistent wall temperatures, but we have the ability to go in and look at your mold temperature. So this is actually the face of the mold temperature at the end of cooling, and we can actually measure and probe different areas of the mold and see where we have unequal mold temperatures in our studies. So in this case, we'll go back in and look same way. So I'm looking at the absolute value in the Y direction. It's still with the indicate, but I've run the cool study on there. So our results are a little bit different than the previous setup I had because I ran the cool study. So it does account for some of that. So my next study I ran, I wanted to show how the effects of having your mold temperature different from one side to the other. So you can also control the way a part warps with your mold temperatures. So if you have one side of your mold is hotter than the other, you've got a non-uniform mold shrinkage. Well, the part will tend to try to shrink toward the hotter side of the mold. So during your process, sometimes an injection molding setup guy will set your mold temperatures on one side of the mold hotter than the other just to have it shrink the other direction. So that's what I've done in this case. Go back to my cool. If we look at our mold temperature at the end of cooling, you see my top water line is set up with hotter temperatures. So we're seeing a hotter mold on the A side, and you see the difference in the mold temperature from one side of the part to the other. So we'll go back in and look at our stress displacement in this case as well. In all of the other studies and everything, we've seen where our curve is basically going across the part, kind of a concave shape, but this one actually, if we look at it, it's trying to curl up on this end too, toward the heat on the mold. So it's actually changed the way the part is warping. So this is actually showing how the plastic software can interpret your cooling lines if you're having problems in an existing mold, and you can put all your settings in this and see where your mold temperatures are different all the way across the part and all the way across the mold. I also ran another study switching the heat to the other side, so we can look at our cool results for the other side of the part. So now we have cold on the top side or A side of the part and the heat on the bottom side of the part. Our warpage again, same directions. And that one actually seems to act a little better than the previous one. So we can see it actually curls a different direction. And this area actually, instead of bowing up, is pulling down toward the heat. So that shows all the different methods that a mold designer or a mold process technician would utilize to be able to control warpage in the injection molding process. We can simulate all of that within the SOLIDWORKS Plastics software ahead of time and have all these decisions made before there's any steel cut in the tool. Or if there's problems with existing molds, as I said, we can put all these parameters within this and actually do some diagnostics and setup checks beforehand without having to be in the machine and taking the mold in and out of the machine. And that concludes my webinar on SOLIDWORKS Plastics and plastic part warpage. Thank you. This has been Jeff Lendermon with GoEngineer.